Let's compute the expected value and the variance of Poisson distribution. In this case, we have Poisson distribution. So we have some random variable x with Poisson distribution and parameter lambda. We know that lambda is some number which is greater than 0. And the PMF of Poisson distribution, so the probability that x equals k, is given by this formula right here. So we have e to the minus lambda, lambda to the power k divided by k factorial, and k is any natural number. So k is any natural number because all the possible values of Poisson distribution are all natural numbers. So if we want to compute the expected value of this discrete distribution, all that we have to use is the formula that we know for the expected value of discrete random variables. So here we will have the sum, and the sum will be over all possible values of x. So we have from k0 to plus infinity, because we know that k is any, k takes value over all the possible natural numbers. And then we have k multiplied by the PMF of the random variable x, so the probability that x equals k. So we just have to compute this sum, and that will be the expected value. So let's do it. So we have here that this is equal to the sum. So first, let's just replace the PMF, so the formula that we have right here. So we have the sum from k0 to plus infinity of k multiplied by the probability that x equals k, which is given by e to the minus lambda, lambda to the k divided by k factorial. So here we have k factorial. So the next step is just to notice that here we have k, here we have k factorial. So we know that k factorial is just the product of all the natural numbers, starting from 1, from 1 to k. So we have 1 multiplied by 2, by 3, by 4, up to k. So we can cancel this k with the last number here, which is going to be k. And then we also can notice that then the sum is not going to be from 0, but the sum is going to be from 1, because if we have 0 right here, so if we replace 0 in this expression, then the whole thing becomes 0. So we can forget about the case when we have 0, because it's equal to 0, and we can start the sum from 1. So let's do that. So we will have the sum. It starts from 1, so we have from 1 to plus infinity. And then we'll have e to the minus lambda, then lambda to the k, divided by k minus 1 factorial. Okay. Now look, we can notice here that we have this e to the minus lambda. This doesn't depend on k. So e to the minus lambda for us is some constant. So we can take this constant out of this expression right here. So let's do that. So we have the sum from k1 to plus infinity. We can write the constant right here, so e to the minus lambda. And we are left with lambda to the power k divided by k minus 1 factorial. So the next thing that we have to do is that we have to notice that this is very similar to something that we know from calculus, okay? But it's not quite enough what we need, but we can make it look like we need. So here we have k minus 1 factorial. So I want to have here k minus 1 as well. So if I want to have here k minus 1, then let's have k minus 1. But if I have a minus 1 here, so if I wrote minus 1, then I have to write plus 1 as well, right? So that I have k plus 0. So I can do that. Everything is okay. So I have now lambda to the k minus 1. But I also have now multiplied this by lambda. So, but lambda is going to be a constant. So I can take just this constant, so the lambda, the extra lambda that I get right now, and I can write it outside the sum as well. So let's see what we get. So we have e to the minus lambda, and then lambda. So this lambda that we obtain from this one right here, and then here we have the sum from 1 to plus infinity of lambda to the k minus 1 divided by k minus 1 factorial. And finally, we've come to the last step. So right here we need to solve this, and we can notice that this is actually a famous expression from calculus. This is just the power series of the exponent. So this is going to be equal. So all of this we know from calculus that this is just e to the lambda. Okay, so the whole series right here, this power series is e to the lambda. So look, we have e to the minus lambda multiplied by e to the lambda. So we know that this is e to the minus lambda plus lambda, so e to the power 0. So this is 1 So we actually have here 1, and we are left with just lambda. And then we get that the expected value of x of Poisson distribution is going to be just lambda. Now that we have found the expected value for Poisson distribution, we can move to the variance. So here we have the formula for the variance. We know that this is the expected value of x squared, or in other words, the second moment. We also call this the second moment of x, minus the expected value of x and the whole thing squared. So from here, we already know the expected value of x. We already proved that this is actually lambda, okay? Now, all that we have to find is the second moment, so the expected value of x squared. How are we going to find this? So look, the formula is very similar to the one for the expected value, but in this case, so before we had that the expected value was the sum, right, from k0 to plus infinity of k multiplied by the PMF. Now in this case we have almost the same, but we don't have k, we have k squared. Why we have that? Look, here, since we have x squared, so we know that the formula for finding, so in this case we can imagine that this right here is just some function of the random variable x. So this is some f of x. Okay, so whenever we need to find the expected value of a function of a random variable, we need to write exactly the same that we have right here, but instead of k, we need to write f of k. So here we had to write f of k. So since the function that we have is being, so f of x is going to be x squared, then here we had to write k squared. That's the only difference. This is something that we know from the properties of the expected value. So all that we have to do now is to compute this, and then we can put this value right here, and then we can find the variance. So let's do that. So look, let's first, as always, so let's replace what is the PMF right here. So we have that this is the sum from k0 to plus infinity of k squared and e to the minus lambda, lambda to the power k divided by k factorial. Okay, so the first thing that we are going to do is that as we did for the expected value here we have k multiplied by k, and here we have k factorial, so we can cancel one of these k's. So this square we can cancel with the last k from the k factorial, and we will have the sum. So by now let me write from k0, but we will understand that actually it's not from 0, it's from 2. So here we have the sum from k0 to plus infinity of k by e to the minus lambda, lambda to the k divided by k minus 1 factorial. Okay, so we obtain almost the same that we obtained for the expected value, but the difference is that right here we still have k. We still have k, and we have to do something with that k. So look, let's do the following trick. But before that, let's understand what we need to write here. So look, if we have k equals 0, then this is going to be equal to 0. Okay. So the sum is actually from 1. Okay, I'm gonna write that next. So look, let me do the following trick. This k right here, I'm gonna write not just k, but I'm gonna write k minus 1 plus 1. So I will have k plus 0. So this k, I'm going to replace it by k minus 1 plus 1. Okay, I can do that because this is k plus 0. So what do we get? So I'm going to divide the sum into two different sums. So the first one is going to be the one containing this, and the second one is going to be the one containing this one right here. Okay, so let's do that. So this is going to be equal. So we have the sum from k1 to plus infinity of, so the first thing that we have is k minus 1 multiplied by e to the minus lambda, lambda to the k divided by k minus 1 factorial, and then we have the sum from k1 to plus infinity of e to the minus lambda, lambda to the k divided by k minus 1 factorial. So look, something from here is very familiar for us already. So this is actually exactly the same expression that we obtained for the expected value. So since this is exactly the same expression that we obtained for the expected value, then this is just the expected value of x, which we already know, we already proved that it's just lambda. So we know that this, right here, this is equal to lambda. Okay, so we already found this, so we just have to repeat everything that we did for the expected value. Now we have to understand what to do with this. Look, here it's going to be very similar, because here we have k minus 1 and here we have k minus 1 factorial. So we can cancel this k minus 1, and here we will have k minus 2 factorial, but moreover, the sum right now is not going to be from 1. The sum, so if we replace k equals 1 right here, then we will obtain that this is going to be equal to 0, just this part. And that's why we can change this 1 here by 2. So we will obtain the following, that this, all of this is equal. So this will be the sum from 2 to plus infinity of e to the minus lambda to lambda to the k divided by k minus 2 factorial plus lambda. Great. So we are almost done right here. So we have lambda right here, and we have this expression right here. So this is very similar to this, right? This is very similar to this. But so how did we solve this? We solved this doing the following. So let's write here plus 1 minus 1. Yes, plus 1 minus 1. And then we obtain that lambda outside, and then we just had the power series for the exponent, and we can cancel the exponent. Now here we don't have k minus 1 factorial. Here we have k minus 2 factorial, so we need k minus 2 right here, and the power of lambda. So we will have just lambda to the power k minus 2 plus 2. Yes, minus 2 plus 2. So this lambda square will be a constant. We will take out this constant right here, and then we are left with this constant e to the minus lambda, and the sum from 2 to plus infinity of lambda to the power k minus 2 divided by k minus 2 factorial. And this is again the power series of the exponent, so this is e to the lambda. So this is e to the lambda multiplied by e to the minus lambda, so this is equal to 1. So all of this will be equal to just lambda square. So lambda square multiplied by 1, so lambda square. So we have finally found that the second moment of Poisson distribution is given by lambda square plus lambda. Lambda square plus lambda. So look, now we can replace that value over here, and we can finally find the variance. So this is going to be equal to lambda square plus lambda minus the expected value of x, which is lambda square, so lambda square. And we get that, well, we can cancel this lambda square with this lambda square, and we get that the answer is just lambda. So actually, the variance for Poisson distribution with parameter lambda is going to be lambda as well. So we have that the expected value is lambda and the variance is lambda.